There we go. Something might be happening now.
All
right. We will see what we will see. All right. It looks like a whole new thing started up.
Well, a new YouTube session.
Yeah. It says I'm broadcasting now, so we will see. That event got hosed somehow. Yeah, somebody's there. I think it's on my main. I think it's on my main channel. It says 15 watching now. All right. Well, guys, we are having fun with YouTube today, among a great many other things.
Yeah, I see it on YouTube now.
You see it now? Okay,
yeah.
John. All right, good. I don't know. There we go. Good. Okay, it says I'm streaming on Deep Astronomy, the main channel now. So that's not an event. All the links I sent out are useless because of this. So that problem seemed to be YouTube, folks. Okay. Well, I'm going to pretend the Hangout just started. So I'm going to go and I'm going to put up this. Yay. So we can see. This is our opening slate. How to process images through your telescope. All right. So what are we doing today, folks? Hello, everybody, and welcome to this month's it's our first Telescope Talk Hangout. My name is Tony Darnell. I work at deepastronomy.space, and this is the Hangout where we are going to talk amateur astronomy. We're going to talk about observing through telescopes, giving advice on buying telescopes, and even taking images through telescopes and processing them later. And that's what today's Hangout is going to all be about. This particular episode, or last episode, we talked about imaging basics, what you need to get started with your telescope in the field of imaging. It's not easy, and it's not cheap, and it's not a beginner's activity, but we give you some groundwork on how you can do that yourselves, get started in imaging. And today we're going to talk about, well, what do you do when you've got a computer full of images that you've taken through your new computer equipment or telescope equipment that you just bought based on our advice. And now, what do you do next? And we're going to be talking about that today. I was going to go into a bunch of stuff about the SpaceX launch I went through yesterday, but we're so late getting started, and I don't want to do it now. So I especially don't want to go over it all over again. I'll post a video about it here in the next day or so to outline my experience. Interact with us, folks. If you found us, great. There's the live chat on YouTube, but more importantly, there's our Discord app, our Discord server that we are I'm looking at right now, which is a really great way to interact with us because the stream stays active even though the chat stays active even though the stream's not happening. So that's why I really prefer doing that as well. I've got Discord here. I see Uncle Bill. It's good to see you again, Uncle Bill. Cosmic Lettuce has been awesome. He was right there yesterday. Peter Q, the Newcastle. Hey, check this out, Peter Q. Right here, Newcastle United. I know they suck. They're in like 16th. Okay, but still, they're not being relegated. That's all I'm going to say on that. Okay, hey Adam, and my guests, my co-hosts, as they always are, let me introduce them now. From top to bottom, we have Alex Reinders in Germany in the upper left. Hi, Alex. And the upper right, we have Adam Smith, who joins us each week. Hi, Adam. And down below is our pub attendee extraordinaire, John Suffill. Hi, John.
Hello, everyone.
Okay, before we get started, let's go back to last week's Hangout. We talked about imaging. John wasn't here for reasons that he may not want to disclose, but he did have something to add to our discussion. So, John, why don't you go ahead? Yeah, Michael Jobin and you guys are showing up, so you guys are back. So, thank you guys for finding us. Sorry about the YouTube problems. That one's not my fault. Okay, John, you wanted to add something to our discussion last week on imaging. You want to go ahead?
Yeah. Now, Alex takes some fantastic photos. I'm really jealous about them.
He does take really good.
His telescopes ever cost thousands of dollars. His mounts cost thousands of dollars, or pounds, or euros. And these cameras cost thousands of dollars, pounds, euros. You don't have to spend that much. You can get a complete setup, a telescope, equatorial mount driven, it must be, really, and a camera for well under £1,000.
Hang on. A camera and a computer or a telescope for under $1,000. What kind of camera are we talking about here?
Well, I've got some here. It's astro cams. If I can share the screen.
All right, hold on just a second. Let me get the...
which one is it? Oh,
share screen. It's down at the bottom of the... See where it says share screen? It's down at the bottom of the teleconference. There you go.
Yeah, but it's not letting me choose the screen. Ah, there it is.
All right, here we go.
Now, this one on the right here, on the left here, sorry, a ZWO colour camera, just under £90.
Okay. Where? Hold on. It says, all right, you are at a place called telescopehouse.com, and you're looking at a color camera for £90. Wait a second. It's a truly affordable color camera for solar system. Oh, it's okay. Imaging featuring low noise and speeds up to 330 frames a second. So this is like and it's got an eyepiece adapter already a part of it. That's really cool.
Yeah,
John.
that's the eyepiece adapter. It's for a 1¼ inch tube, and so that you can see it's not going to be very big. It looks superficially like a normal 1¼ inch eyepiece, except instead of a lump of glass that you look through, it connects to your computer via USB, and you take the images through that.
Okay, now this is part of the imaging thing that we didn't talk about last week, and I thought, and the reason I didn't bring it up was I was worried about these. This was what webcam imaging, or at least this is a derivative of that, and I was worried that those webcams that they make nowadays wouldn't even be up to it. I mean, the kind of webcams you have now are these kind, that go. These are CMOS detectors and things like, and they're not very good for attaching to a telescope. So I didn't bring it up, but you are showing me stuff that is exciting. I didn't know these were out here. I don't know if they're available in the States, folks. I'm going to have to look this up, but webcams, of which this is, it looks like it's got a small sensor. It doesn't say if it's CCD or CMOS, does it? It's CMOS down there at the bottom. Okay. Now, the reason CCDs tended to be better than CMOS cameras, folks, was the way they were read out. They had a lot less readout noise, and CMOS cameras at the time, while they have fast frame rates, were very poor with their low light qualities. But apparently they've gotten better. So, well, I don't know. What do you think, Alex? Have you seen these? You're muted.
Alex?
Yeah, now I am. You can hear me?
Yeah, we can hear you.
Yeah, we can hear you now. Yeah.
So what was the question?
The question is, what do you think of this?
They are good for planetary imaging.
No, I mean, what do you... Yeah, we're going to get into what they're good for in a minute, but I just want to know what you think of this camera. You think it's pretty cool?
They are cool. Yeah. And you have to have right weather and the right environment. You must not have any houses in your environment, because heating will make the seeing bad, and you need for this kind of imaging quite a good seeing. I tried this here from my house, but it never worked really good, so I don't use these at home.
Okay, so you've got other cameras which you showed us last time as well, some DSLRs and things like that. Okay, well, Thanks, John. This is good. Now, the reason that so Alex has already given you some problems with these, and the others are that they really are not very light sensitive, and they really require, you can only really look at bright objects with them, like the moon and the planets. And if you have a special filter, you can do solar imaging with them as well. They're really good for things like that. But deep sky, long exposure photography, they're not that great. But I will say this, and we should probably have a hangout on this, guys, when it comes to what I call webcam astro-imaging. They do have, given all the caveats that Alex just mentioned, they have the great benefit of being the poor man's adaptive optics. And why is that? Well, they have high frame rates. Basically, they just take video over the eyepiece, and then they store those as individual frames on your computer. If you then go by with software, which we're going to talk about in just a minute, and go through those frames, it will throw out all of the ones that have crappy seeing or the smudging or whatever, and only keep the crisp, clear, and you can set all these thresholds, crisp, clear things that images that are left behind. And when you add those together, you get pretty nice images. I used it back in the day with an old Philips CCD webcam, 640 by 480, on my telescope to image an opposition of Mars, and it came out really good. I was really pleased at how well it worked. So yes, you can get into this for under $1,000, John. That's a good point. But you have to, with the caveat of what Alex said, you need good seeing, relatively dark skies, and then you still got to do a heck of a lot of post-processing after the fact.
Oh, yeah. You need much more hardware. You need hard drive. You need a fast computer for processing this stuff, those videos. It's easy to get 7 gigs for one video on one shot in maybe 2 or 3 minutes. It depends on the pixels that you use. And additional to say is little webcams that got a very, very small chip, and it's a very, very small cutout from the picture you get of the scope. So it's more for details.
Right. And did you want to add anything else to that, John?
Well, yeah, Alex is right. If you viewfinder, if your eyepiece is going to give you an image like that, one of these cameras will give you an image around about that. So it's very tight, very centered.
What do you mean, as far as the actual size of the image itself? Right, yeah. Because those, I didn't see what the dimensions were on that sensor, but you're looking at 640 by 480. Sometimes you can get a little bit higher up in image quality or in resolution, spatial resolution. But yeah, you're right. It'll be a tiny image for sure. And
if you look at something like Sky at Night magazine, they have photos taken by amateurs. Quite a lot of the time, they'll be using cameras like that.
Right. Yep. And
so you can get really good photos from them.
And Sky and Tel here in the States would be a good magazine for checking that out too. So cool. All right. Well, good. Thank you for that, John. I appreciate it. So yeah, you can get into image. All that other stuff still applies, though. You still need a sturdy mount, because God knows you've already got to deal with the roiling atmosphere. You don't want to be mounting that on a toothpick of a tripod and have it being blown all over the place. So you still need a sturdy mount. You still need a good clock drive, preferably with a go-to system, because those, as John pointed out, they don't have wide fields of view. It's like looking at the universe through if you have an eyepiece, it's like looking through a universe through a straw. But if one of those, it's like you looking through the universe through a coffee stirrer. You get a very narrow field of view. So you need a highly accurate telescope mount. Excuse me. So anyway, good advice. Okay, now you got a computer. You've done this. You've bought your stuff. You bought your mounts. You've got your go-to system. You've got your cameras. You bought a really cool DSLR like what Alex has. And you've connected it all up to your computer. You pointed it at Mars or Jupiter or Saturn, and you've pointed it at the Orion Nebula, and you've got all this stuff. Well, if you look at the individual images, it's not going to be that great, is it, Alex?
It's not that great. You're right.
You need to do something.
Maybe I can show an example of easy way to start. It's again You see that using your DSLR.
Yep.
Just that tripod and the camera. And you don't need any guiding for doing stuff like this. This is the program Star Trails. And it adds by the time if you do some Star Trail photos, pictures, it adds image by image, and then, yeah, it did quite a good picture of Star Trail.
Now, wait a minute. Is that your final image?
No, it's just processing now.
That's just what you got out of the camera, right?
Yes.
Okay. All right. Well, I want to take let me just take a quick step back here and say that so there are, regardless of the imaging system that you've bought, regardless of whether you got one of John's 90-pound or 90-euro cameras or you have one of Alex's $5,000 cameras, you got to do the same thing to all your images no matter what. Now, we talked a little bit about dark current, but we're going to introduce a new concept called flat fielding. Now, as John has pointed out, or I'm sorry, as Alex has pointed out, when you take these images, they look like crap coming right off the camera. And the reason for that crap is a lot of things. We talked about dark current. Whenever you leave an image open and the CCD active and it's collecting photons through its optical system, it is also collecting noise from the camera itself. That's called a bias. That's just electronic noise. And it's also getting noise from heat. Heat is building up in this sensor, and unless you keep that sensor cool, you're gonna have a heat buildup that looks like just a bunch of snow. Alex, do you happen to have handy a dark image, an image of just a dark?
Yes.
So what you need to do while you're out there at the telescope, you're going to have to expect all of these things that are going to happen. And so while you're out there at the telescope, you want to take 3 different images through your telescope. You want to take a dark image that equals the exposure time of the other images that you've taken. So if you've taken a 10-second exposure of Mars, you need to also take a 10-second dark.
Here we are. Here's the tool.
You also need to take a...
Now, this is a dark. It's about 20 minutes or 30 minutes. And yeah, if I do this, I see all the noise, the signal noise from the chip. While exposuring for maybe.
Can you
20
scale
or
it
30
a bit more, because it's looking, all I see
Yes.
is dark. Scale it so we can see the noise better.
You see that noise?
Yeah.
Not really.
See now?
I don't see it that much. Can you see? Oh, share your screen. Where'd you try sharing your screen one more time?
Try to reshare it.
Yeah, it wasn't coming through.
You see that?
Hang on, I'm still waiting for it to come through. Yay, internet. All right, well. Huh. Gosh darn it, there's all kinds of problems today. I don't see it.
I do, strangely.
Do you see it?
Yeah, I see it, yeah.
It's probably me. Can you try one more time, just unsharing and sharing it again?
Yes.
Thank you.
No. Once again.
It just says you're sharing your screen. All right. Well, you know what? Oh, wait. It's showing up on the stream itself. So, no, it's not. Okay. All right. I'm sorry, guys. I'm trying to see the image that he's sharing a screen for, and you seeing what I'm seeing. Can't be me. I've got bandwidth this time. All right. Let me do this. I don't know how to get your screen. All I'm seeing is Alex has started sharing screen. Double click to enter view screen. That's all I see. And I don't see anything else.
But I think people have seen the snow here.
All right.
I put the brightness up, and yes, that's a dark. That's signal noise from an exposure you take at night. You take these exposures as you did your lights, your raw pictures, but just without incoming light. You just put a cap on it on your scope or something at night at the same temperature. That is important because more temperature means more signal noise on the chip you're using. And yes, you take 5 or 6 per night after your exposuring. And what also important is using flats.
Okay, don't go there yet. Hold on. All right, so what you should be seeing, but you're not, is a snowy screen, okay? All it is a picture with the cover, with the lens cap on. Imagine that. You put the lens cap on, and if you took a picture of, say, 100 seconds, that is what you would see. It's just snow. It's just white noise. Some pixels will be brighter than others. Some will be darker. But it's an important image because you need, as Alex said, it needs to be the same exposure as what you're taking a picture of. So if you're taking a picture of the Orion Nebula at 100 seconds, you need to have a corresponding dark image of 100 seconds also, because that is a measure of the dark current at the time you're doing it. And it's important to do it on the night that you're observing because you want to get the same temperature. Ah, finally I see it. There it is. Bless you. That's it. Ah, there it is, folks. That's it. That's a dark. Yes, thank you, Alex. Thank you, Zoom. Thank you, internet gods, for letting this happen. It doesn't look like much, but it is important. I'm just going nuts today. That image will then, that is the noise right there of all of the CCD at the time. It includes bias as well as dark. And that is the thermal noise of Alex's CCD. And so and as you can, it also has hot pixels. Some hot pixels are just pixels that are always on. It's hard to tell which are which, but that's an important image to take, and it needs to be done.
I can show you a bias too.
Yeah. Okay. Go ahead and show a bias. A bias is the measure of the noise in Alex's camera, and that's just the readout noise. That's the electronic noise that comes from all of the pixels. Every camera has it. I don't care if you spend $1 billion kajillion on it. The DE cam and the 4 meter Blanco camera has it. The Hubble Space Telescope has it. The James Webb Telescope is going to have it. They all have this. That right there. That's beautiful.
It's actually a must-have.
Yes, that's actually gorgeous. That is a measure of the noise, the electronic noise in Alex's camera. And you see stripes, and you just can't get rid of it. I mean, it's always present, but you don't want it in your final image. So you're out at the camera, you're out at the telescope, you're taking your Orion Nebula picture. You also need to take this, which is called a bias. How do you take this bias, Alex?
It's the same ISO, the same sensitivity as you did your light pictures or your raw pictures, and everything must be done in the raw format. Don't do it in the JPEG format, because then you're losing data. Ah,
that's a good point. Every camera has a native format. If you output in JPEG, then the camera has done some processing and compression on it. You don't want that. You want the raw data itself, whatever format that happens to be for a camera. Now, a bias is basically just a really, really short, a few tenths of a second, exposure image of a dark. That's all it really is. You just don't want there to be any thermal noise. You don't want there to be any thermal noise built up yet. So now you've got a bias.
I can't hear you.
That's probably my internet, but I'm still streaming. So we have a bias, which is the measure of the electronic noise. We have the dark, which is a measure of the thermal noise. You need one more image before you're done at the night at the telescope, and that is a bias. I'm sorry, a flat field.
A flat.
Can you show us a flat?
I only have good flats, but well,
we only want to see good flats.
I don't have any dust on it.
Okay, this is a slightly different image. Hang on just a second.
Yes, you can see the vignetting a bit.
Ah, okay. So yeah, you can see
right
it
in the center, and it's going darker to the edges.
Wow, you don't have any dust donuts or anything.
No.
Wow. Oh, you sound no. I'm really good. That's because I keep my optics clean, Tony. That's funny, Alex. Okay. So what? You want to describe? What is that? Oh, that's what you clean.
This is against dust. You must have this. This is one of the most important tools in astronomy. You get rid of dust on eyepieces, on optics, and on PCD chips and camera chips and anything else. It's one of the most important tools you can have on astronomy. This little apple. I promise.
That's a good point. Yeah, those little dust blowers are
Yes.
ideal. So that's good advice. Okay, can you put your flat back up?
Mm-hmm.
All right. Now, a flat is a different kind of image altogether. Alex, do you want to describe how you take a flat, or do you want me to do it?
Again, the raw image, the raw file.
Right, the raw camera format.
Yes, I have, yes, how to call it, lightning foil for most homogeneous lighting in the front of the optics, in the front of the lens. And you just put it on, and then you go to automatic exposure on your camera in the RAW format. You can use your internal dark function on options, and yes, you can take 10 pictures, for example. And then you can clear out or take out the dust on your light pictures or vignetting. And this is very important, maybe more important than taking darks.
Right. Now this, folks, is the, forgive my French, but this is a bitch of an image to take. At least it always has been for me. So here's the thing. As Alex said, you want to illuminate the surface of something as evenly as possible. What you're trying to get a picture of is all of the imperfections in the optical path, all of the dust, all of the light reflections, everything else. Now, Alex doesn't suffer from that because he keeps his optics very clean. But if you had a piece of dust on any of the surfaces, it would show up as an out of focus donut. I call them dust donuts. A lot of, well, I don't just do what everybody does, but but there's also things like imperfections in the way the camera responds to light. That's why what I used to do was take a white cardboard poster board, tape it up on the wall, and shine a light onto it, just like a halogen work lamp. And then I would point after I was done for the night, I would after I took all of the images, I would point that telescope toward the poster board and take a few very short exposure photos of which is called flat fielding. Now, a lot of people, sometimes people will just put their telescope way out of focus and then point it at the sky at a brighter, like if it's twilight or if it's evening before the sun sets or before the sun rises. People will take their telescope and take what's called twilight flats, or dawn flats, whatever you want to call them. And the reason but they're not ideal because they have a gradient on them because of the night sky that's brighter toward the sun and dimmer toward the other parts. So they tend to have a gradient, which isn't ideal. You want a nice even photo, like what Alex does have. Off toward the right there, you can see a slightly brightish spot, but that's not so bad. I mean, what you're mostly after is getting the imperfections in the image. That's a flat. That's a really good flat, Alex. Very good. And now you've done. Now you're finally done. You've been up all night. You've been imaging like crazy. You've taken all of your images, but before you left, you remembered to take a few bias images. 5 preferably, and I'll tell you why you should take at least 5. And then you took all of the darks that you needed for all the exposures, all your 10-second darks, all your 50-second darks, all your 100-second darks, and you put them together into a special folder, and you call them calibration images. And then you can close down your telescope for the night and go to sleep because you're too tired to process. Unless is that what you do, Alex, or do you stay up and process?
Yes.
Oh, you go to bed.
Everything automatically, just programming, before going to bed, and then before leaving the house in the morning, I switch off the telescope and then I'm done. And when I've got time, maybe at weekends or something, I do some image processing.
Right. Now you're ready to start making pretty pictures, and you need some software to do that. Before I get to the different kinds of software, I just want to say that the way you correct using these images, whether you've got a dark, a bias, or a flat, is all done differently. The bias and the dark are additive corrections you need to make, which means that they add imperfections to the image. So to remove them, all you do is subtract. So you have to take your main image and you subtract it by your dark image, and you also subtract the bias image. And that will remove any dark current and bias noise that you have from your image. The flat, however, is a multiplicative effect, meaning that when the way you would the imperfections are best removed by the inverse of the image that you've taken. So if you've got a dust donut that's causing a lot of problems, the way you want to get rid of that dust donut is divide by it, and that will bring it back up to 1. That is a multiplicative effect. I can't really describe it other than if you can imagine a little light curve of your dust donut going down, dipping down a little bit, the best way to remove it is to divide by its inverse, right? Or to multiply by its inverse, which is divide. And that will make it nice and flat and remove exactly those imperfections. So you generally divide by your flat field. And that is your basic instrument corrections. It's a lot of work. If you're saying to yourself, man, I don't know if it's worth doing this. I mean, you got to really ask yourself that question. Now, for Alex, the results are worth it to him, right? I mean, you go through all this work all the time.
Yes,
how long does it usually take you, Alex, to process one image that you're happy with?
Oh, yeah. Mm-hmm. I know a guy it took 4 years for one image.
Yeah.
And after 8 hours, I'm done. I don't want to see it anymore, you know.
So, right. I mean, the steps we're talking about are just the basic steps. Then you get it into Photoshop or whatever it is, and then you go nuts, right? I mean, you can split it up into different filters and all of that kind of stuff. So, okay.
Do you have a program for stacking, Alex?
Yeah, good idea. Let's talk about software.
You can use Deep Sky Stacker. That's a free program.
Deep Sky Stacker?
Yes.
Okay.
But I am using Images Plus.
Images Plus?
Yes.
Okay. Tell us about those programs. Tell us about Images Plus.
Now it is. Here are my light frames. Here are my dark frames. The flats. That darks, I don't use them. And yes. And I go to the processing. Saying, oh, what do I take? For example, this USLR, light processing, getting the noise out, using standard default settings. Then I use the maybe sigma average for combining all these pictures. Save that mode, saying minimize on the hard drive, align the stars, combining the pictures. Yeah, doing the grades, normalizing the pictures, extra filters, for example, like noise. And then I start processing.
Is this free or does it cost money?
This costs about $150.
Okay.
How many images are you processing there, Alex?
5.
Now 5.
All right.
5 lights, 5 darks, 5 flats, 5 bias.
All right. So you've already told this program what your images are, the object images. You've told them what the dark frames are. You've told it about your flats, and you've told it about your biases, right?
Mm-hmm.
And it takes all of those images now that it knows what's what, and you hit a button that says process, and then you go to bed or get a cup of tea, and off it goes and does things. And this is great. This is really great. Now, if you don't want to spend money, there's another one called Registax, which is out there. And it runs on Linux too, which I really liked. Mm-hmm. And that will not. Well, yeah, it will. I think it will. It will do bias corrections and stuff like that, and it will register your images and add them up as well. And it's been around for a while. It's free. It has that advantage too, and I just did a quick search on it. It's still available. That's what I used, was Registax, Registax.
There's also Giotto you can use.
Say it again, please, slowly.
Giotto, Giotto.
Oh, I haven't heard that one. Okay, yeah. So there's lots of free stuff out there too. Definitely experiment with that stuff before you spend any money.
Fire capture is also nice.
Say it again.
Fire capture. That's
File capture?
very good for planetary imaging.
Oh, okay. All right. Now, let me explain something to you that's very important about imaging in astronomy. You've all heard me say many times with the Hubble Space Telescope that when they made the Hubble Deep Field, they stared at the same patch of sky for 11 days. Now, what I mean when I say that, and what they mean when they say that, is they didn't just point the telescope to the area of the Hubble Deep Field, open up the camera shutter, and go away for 11 days. What they did was, over the course of a time, they took a bunch of images of the same area of sky. About 100 seconds was the exposure. And they would stare at it for 100 seconds, take an image, take 100 seconds, take an image, 100 seconds, take an image, 100 seconds, take an image. Then they would go do something else. They would go look somewhere else for some other astronomer, and then they would take a bunch of images for that astronomer, and they would follow their schedule, and then they would go back to the deep field area of sky, 100 seconds here, 100 seconds here, 100 seconds here, and then they would go do something else. They did that every 100 seconds that they looked at that sky added up to be 11 days worth of exposure time. And that's how everybody takes images over a telescope, because there's an advantage to looking at the same patch of sky for a short period of time rather than looking at that same patch of sky for a long period of time. We've already told you, these cameras have bias, electronic noise. They have thermal noise. I don't care how cold you keep it. You leave it open for a day, all you're going to end up with in the final analysis is you're going to see a dark image, or you're going to see saturated noise, okay? It's not going to be good. So you have to keep the noise down and the signal high. And the best way to do that is to take short exposure photographs. And then, at the end of the day, you add them all up. So let's say you took 100 100-second exposures. You now have 100 times 100 seconds as an exposure time. You add them all up. This is a very well-known image processing technique. When you add these images up, the signal adds up as the number of images you've got. 100 times, if you add 100 seconds of 100 images, you get 100 times more signal. But the noise only goes up as the square root of the number of images, as the square root of 100. So even though you add up all of those images, the noise is only adding up as the square root of those images. And that is why everybody takes short exposures and adds them up. With computer programs like what Alex has here, it's trivial to register each image because each image is going to be slightly different. But they register the images and add them up. And they do it within a pixel of accuracy. So they do a really good job. And by adding them all up, you get a high signal and low noise. And of course, before you add them all up, you subtract out your dark frames and your bias frames as well. So that is another thing you need to be aware of. And when you're planetary imaging, like what John showed you with those webcam kind of cameras, it's even more important because you're going to get this fuzzy little, very dim thing. But when you add them all up, you get a much brighter, higher resolution thing. Okay.
I could add here that I don't know how many photos Alex takes when he's doing something like the Orion Nebula or something like that. But with one of those webcams or the astro cameras, he could be taking the equivalent of 1,500, 2,000 frames.
That's right.
And then he then you use another program. A favourite one is called PIPP. You select one of the images, and you tell the program to delete disregard any image that is worse than that one. So you cut it down to about 200, 150.
Okay, that's a good point. Those video images are going to if you take 1 second of video it's about 30 frames a second, those things usually go at. So you've got 30 frames per second times however many seconds, that's a lot of images. Now what Registax does, and I'm sure your program does it too, Alex, is you can have parameters where it will go through all of those image stacks and it will say, you can throw them out if they're...
Yes, you can say take 50% of the sharpest or 20% of the sharpest pictures. And then you get images from planets like you seen from Voyager, for example.
And that's what I meant about a poor man's adaptive optics, because you're going to get a lot of crap in with the good stuff, and it'll just automatically throw those away. So is this image that you're showing now, Alex, is that the result of your processing?
This is the result, and now you can take all those gradient levels and play with it and see how many details you can get. This is the image you get after processing, and then you are processing a bit with the gradients of the picture, and the more data you have, the more fun it makes.
Right, because you have more signal.
Yes.
Right. And so that's beautiful. That's a nice star field. Look at those stars. Those stars are nicely pinpointed. They're very well registered. I don't see
here.
The edge of the field has a little bit of slightly elongated stars, but it's not too bad. I mean, it's really a nice telescope, Alex. So
this is a L407. This area here, in the middle, these galaxies here, these elements and galaxies.
Okay, so let's say for a minute that Alex, when he took this picture, he took these series of pictures. He processed 5. He took his darks and his flats. Let's say he did it in a red filter. Okay, let's say he took all of that with a red filter. He'd have to do it. He'd also have to take his flats with a red filter. But then he would have this completed image that he has here, and he might call it combined files sig average underscore R for that's the red filter. Then he would do the same thing again for the green and the blue filter that he might have. You could do all of this with various filters. They're still going to look grayscale in this, but in this program. But when you add them all up in, say, Photoshop, you get this is what would look like in red. Another one might be what it looks like in green. Another one might be what it looks like in blue. And you add all those up, and you get a color image. And that's what they do at the Hubble Space Telescope. And that's also what I'm sure Alex does when he wants a color picture.
Oh, I take DSLR because, I'm a lazy person. I don't take any colors extra. I just want it all at one shot. And then I just add it. This is why I don't use CCD, for example. You know, if you got a night taking red pictures or the lights, and the green and the blues, and you got a bad weather for maybe 2 weeks, you will have the next chance for taking the blues or the greens maybe next year and not the next month.
Okay.
So something will be missing.
Yeah, that's true. With DSLRs, you don't have to worry about filters quite so much. It'll take color images for you. You're relying on your telescope optics to give you all of the wavelengths equally well. You don't have chromatic aberrations or any of that kind of stuff to mess up your colors. And you can get really, really, really good results that way. However, for scientific use, they tend to put in their own filters because those are well-characterized filters. They actually mean something scientifically. So when you see something very bright in, say, a green filter at a certain wavelength, it means something. It means the presence of oxygen, or it means the presence of something that they're looking for. So scientifically, they're very important. For artistic work, however, this is plenty good. Okay. Wow. So we covered a lot. Don't even begin to get upset if you don't get this, because this is a lot. Okay. And this is a deep topic. Imaging is not
3 years to learn this.
It took Alex 3 years. I've spent a lifetime doing it. I've written so much code. I can't even tell you, how to do this. I want to say something about the chat. Apparently we've had some problems with the chat. I just want to point out, we didn't have any problems in Discord. So if you guys want to continue our live chat or any kind of chat 24/7, I'm not saying I'm there 24/7, but Uncle Bill's there right now. Cosmic Lettuce has been there. Nobody's been doing the chat. Nobody on Discord. I'm just saying this is awesome. And I know everybody loves the YouTube live chat. It's great while we're streaming. Okay? But all that disappears the minute we stop streaming, and we still have our conversation, and we still have our community going at the Deep Astronomy Discord server. So that's why I love it so much. I was able to share all of my experiences yesterday at the Falcon Heavy launch with people who were on Discord. I know it's a bit of a pain. You got to download an app. You got to have a new thing up. But really, all of this stuff has its pluses and minuses. And when you're streaming on 4 platforms, and you want to build a community, I really like Discord. I don't know. Adam, you use it. Are you okay with it? Do you think it's all right?
Yeah. I think Discord's great, yeah.
Yeah, I mean, like I said, I was there all day yesterday, and it really, what I loved about it was when I was at the launch, all my Discord guys were there, and I could just share it with them. I didn't have to go on Twitter. I didn't have to post on anything else. It was just right there, and I knew that we were kind of a Deep Astronomy sort of kindred spirits in there, so that's why I use it so much. Michael Jobin is asking on the live chat in YouTube, having said all that, does anyone use silver emulsion film? No. But go ahead. Not unless we have to. If we got to get some kind of torture going, then maybe. I don't know. Do you guys still use film? You had some film, didn't you, Alex?
Yes. I don't miss it at all.
Yeah, I don't either. Film is messy. Film is yuck. But
yeah, I used to use the old monochrome film and color slides.
Right, Ektachrome, and I used 2415 technical pan film. That was the best for you know how GPS
I missed the darkroom though.
Huh?
I must admit, I missed the darkroom.
Do you? You miss those smell? You just miss getting high on those chemicals, don't you? Yeah, well, you know how the GPS has changed our lives? How we can't do anything without GPS anymore? Well, CCDs did that for astronomy. It got rid of film. And film was great, but it didn't have a linear response to light. It had some kind of weird logarithmic response. So if you wanted to do photometry with it, it was a pain. CCDs, it was very linear in response. So if you got twice as many photons from an object as you did the day before, that meant you could actually measure that flux, and it actually had scientific units, and you didn't have to do this weird math using logarithms to overcome it. So no, I don't think anybody's using film unless they want to, or they like to be tortured, or they are some sort of masochistic person, because you got it just has a lot of problems, not the least of which is its resolution. CCDs beat it by far now.
Wait, can you get films today? Can you buy these days?
Oh yes, you can buy it.
Yeah, you can still get all of it. You can still buy hypering units too. Remember though, where you could hypersensitize? Really? Yeah.
Oh my god.
Yeah, you can still hyperfilm too. God knows why you would, but Galaxy is going, yeah, but we could keep Discord for after and between hangouts. Sure, yeah. I mean, I'm not going to stop anybody from using the live chat. I mean, it's there. It's just, I'm just saying, it's so nice to just have a one-stop shop for all the chats and all the platforms. That's all I'm saying, Galaxy. Of course, you can keep using it. It's fine. All of your chat's going to go away, though, at the end of this stream. So that's the only disadvantage. Wow. Okay, next week we want to talk about some more stuff. What did we say we wanted? Oh! Don't know if we can make this happen. But Alex has introduced me electronically to a guy in Germany who is processing Juno data and you've seen his work. You've seen it all over NASA's websites. He's done amazing work with Juno data. And so I'm going to ask him to be in the Hangout in 2 weeks. And we're also going to ask, I'm drawing a blank. Who else do we want to ask, guys? One other person.
Judy?
Oh, no, maybe Judy Schmidt on Twitter, but I don't know. Or Jason Major, who's a science writer, and he's big on astro-imaging as well. We might ask him to also join us as someone who uses professional data. I would also point you guys back to a Hubble Hangout that I did many years ago with Zolt LeVay. Zolt LeVay is part of the Hubble Heritage team, and his job is to make those gorgeous Hubble photos you always see. And he's talked about how he did it. He uses a program called FITS Liberator. It's free. You can get it. FITS, by the way, is the File Image Transport System. It was invented by NASA for astronomy images, and it's what everybody uses in the world. You don't use it though, Alex, right? Because your computer doesn't have raw. But you could, if you wanted to, take the raw images from your camera and turn them into a FITS image if you wanted to. Did you know that? Oh, I see. My internet's gone bad again. Can you hear me, Alex?
Now I can hear you.
Yeah, that's my internet. So, you know that you could, if you wanted to, take the raw images from your camera and turn them into FITS images. Did you know that? Yeah. It's an extra step, but it's worth doing because the image, the FITS image, has two parts. It has a header, which you can store lots of useful information in, things like exposure time, date, time, bias image, all that kind of stuff. And you can put it all into one image and store all that information right there. It's really quite good. It's been around since the 70s. Anyway, Zolt LeVay uses FITS Liberator to deal with the images, and he also talked about his processing techniques. So do a search on the Hubble Site channel. I don't have those hangouts on my Deep Astronomy channel. And then he gave a great tutorial of how he processes Hubble images into the images that you're used to seeing on the web. So check that out. We're going to talk also about how next time with Jason Major, if he shows up, and the other gentleman from Germany on Juno, how to get images from the massed archive from Hubble to get your own Hubble data, and you can do some processing yourself without taking any images yourself. And that's a topic I want to get into independent of imaging with your own telescope. Alex is showing a nice, pretty image. You want to talk about it?
That's a star trail as a result from the program I run, the Star Trails program. Maybe you can have a try it with, this is good for JPEGs, for example. But much easier than all that deep sky imaging processing.
Okay, Galaxies is saying, I think it's better not to scatter the chat over two main platforms. I suppose so, yeah, but at the same time, once you build a community, and by the way, Galaxia, the less I become invested in one platform, the better it is for me. Believe me, that's why I stream on 4 platforms. I don't live on YouTube solely because if anything happens to YouTube, which did today, then I'm the one that ends up getting hurt. I would prefer it if I had my druthers on all of this, that everybody only do things on deepastronomy.space. That's my platform. I control that, but I'm building it up. But, you know, Discord is a big part of that. It has to do with me being able to control my content regardless of the platform I'm on. And, of course, you know, YouTube chat, I'm at the mercy of these platforms. I don't want to be. I would just as soon like to suddenly decide, you know what, I'm streaming on Joe's new streaming platform, and that's where I'm going to be, and having nobody notice the difference. Because YouTube, while it's great, has its problems, so does Twitch, so does all these other platforms, and it's really dangerous as a content provider for me to get married to any one specific thing. So that's why you hear me doing this, Galaxy. I'm not doing it to make your life hard. I just really, you know, trying to make it better for all of us. Okay, do we make... Uncle Bill's like, I'm on over 60 Discord servers. Okay. I'm not saying do that, okay? It's my go-to one-stop platform. So good. That's a plus for that. Do you guys have any questions? Did we see any questions that we didn't get to? Oh, there's the guy that got booted. Okay. Yeah, about the snow and the need of calibration of the camera, and that every telescope camera has it, even Hubble and JWST. That's right. That's right. All cameras have it. Oh yeah, that guy was weird, wasn't he? Okay, did we get to any questions that I missed, guys, or did we miss anything?
Not so far.
Okay. All right. Well, let's go ahead and wrap it up. We're already over, but we started late. Anything you guys want to add before we say goodbye?
Yes. The longer you take you expose your pictures, the better your data gets. For example, the VLT in Chile observes objects that release about 5 photons per hour. So you need time for exposure, for collecting photons.
Okay, but there's a trade-off, right? I'm sitting here telling everybody keep the exposure times as short as possible. That's always good advice. But those guys are also looking at very faint things, right? So, right. So you got to get some signal, and whatever exposure time gets you that signal is what you need to shoot for. But imagine, how many photons per hour?
5.
So five actual photons hitting your detector over the course of an hour.
Yes. It must be large and big.
You're going to need a big telescope and a really sensitive camera. And you know what else they're doing, folks? They're cooling that camera.
No, it's gone
They're
again.
cooling it to
you.
either liquid nitrogen or liquid helium temperatures. So, yeah. So that has to keep that dark noise down. That's not an amateur thing, I don't think. Do you, Alex? You think that's you think they would...
Just an example for really taking long exposures. And the better the pictures get.
That's right. So the trick is you want enough signal without having the noise overcome the exposure. And that's always a trade-off. You're going to have to experiment.
Down. Yeah. Low sensitivity as possible. And long exposure. That's the best results. For the best results for your pictures.
Right, and that's why you might see better results from a Canon DSLR over a Nikon. They may have individual characteristics that are better at certain wavelengths than others. It may be the the detector they put in it at the time. That's also a good justification for buying an S-Big camera or an Apogee camera, because they're already designed for low noise.
There's a decision to buy an astro camera or a car. You are free to do so. But better use a DSLR. Buy it used, buy new always, and then you're good.
Yeah, if you're getting into it for the first time, a DSLR, absolutely. When you've mastered these other techniques we've talked about, getting the image in the first place, which was the subject of last week's Hangout, then processing the images after the fact, which is subject to this one. Yeah, if you can get past all that, then you might think about doing what Alex is doing, which is spending some serious cash on cameras and things like that. So, okay, well, that is, I guess we'll stop there. Plus, new subscribers may want to follow a few weeks before joining another platform anyway. This and FB or Outreach. Yeah, okay. Well, thank you, Uncle Bill. Thank you guys for another Hangout. Next time, we're going to take this on the road. Not the road. We're going to invite some new people in, if they agree. We'll talk about Juno imaging. We'll talk about imaging from Hubble and massed archives and things like that. If you got any questions, join us on our Discord server, and I'll be there all the time. Wait, here's something. Adi asks on YouTube, can the human eye see all the galaxies in the universe if they are within the visible range, or would our eyes be unable to see them due to its limits? Oh yeah, no. The answer is no. You can't see all the galaxies in the universe with your eye, with the human eye. The human eye is most sensitive in visible wavelengths. It's also got a really teeny tiny iris, which means it doesn't collect a lot of photons, so you can't just look up and see very distant galaxies with your naked eye. In fact, we could barely see the Andromeda galaxy with our naked eye, and that's like, what is that, 2.5? Is it 2.5 million light years? Yeah, million light years away. I always get that confused. The collision happens in 4 billion years. So I always get for some reason I get those numbers transposed. So, but you can't see those images with your eye. You need a telescope to see them. You can't see the distant galaxies. In fact, the reason, and everybody gets really pissed off about this, but the reason JWST is an infrared telescope and not a visible light telescope is that it wants to see those distant galaxies. It wants to see the very first galaxies ever in the universe. Ever. The first galaxy ever to form. That's what JWST wants to see, and it's not going to see it in the visible range. If it had visible cameras on there, nothing. You wouldn't see a thing. It needs to be in the infrared. Why? Because the very distant galaxies have red shifted, as the universe has expanded, into the infrared. That's where they're shining. So to see the most distant galaxies in the universe, all of the galaxies, you need several wavelengths. You need optical for the close ones, you need infrared for the very far away ones, and you also need X-ray and gamma ray telescopes to see the centers of those galaxies so that you can see the gamma ray bursts and the active black holes at the centers. So you need many wavelengths. You need radio to see them as well. And that's what ALMA is doing with radio telescopes. So you need all the wavelengths to see all the galaxies in the universe. Visible light, astronomers don't care about visible light. Only The general public cares about visible light, but astronomers could care less. It's a very uninteresting part of the spectrum. Okay, Johannes Teichert, what about Deep Sky Stacker? Have you guys heard of that?
Yes, that's good.
You've used it?
I used it at the beginning.
Is it free?
It is free. It is very good.
Okay.
Done with it.
Okay, you want to show us what you're talking about there, and then we'll go. What do you got there?
I just want to shock you to the end. It's a price of a CCD camera with 16,000 megapixels, and it costs about 4,000 euros. You got to add your filters for several thousand euros, and just you can easily spend very much money on your cam. And then you got to use your hardware. You got to have a good computer, big hard drive, and stuff. And so you can easily go up with the price or the money you spend.
Yeah, and that doesn't even include the filters, but at least it has a filter wheel, which is nice. And a filter wheel will be something you can control with a computer, tell you what filter to put in. Filters, whole nother topic for a whole nother hangout. We should talk about filters in a future hangout for sure. But yeah, there you go. So
that's a high-end astro camera.
Very high-end, and it has.
How
was it cooled?
That was
How was it cooled, Alex?
The filters.
I'm sorry, I cut you off, John. What did you say?
Astrophotographers, if they're really into it, will use a monochrome camera, and for that reason, the monochrome camera is more expensive than the color version.
Yeah,
because it's more sensitive.
That's right, and yeah, when you're getting 5 photons an hour, folks, sensitivity is pretty huge. So yeah, okay,
go for it.
Yeah, exactly. Okay, so let's see. I was asking something and I forgot what it was. But anyway, all right. I guess we'll stop there. Thank you guys so much for talking with us about telescopes. We'll be back in 2 weeks where we're going to talk about all the things I just said. Tomorrow, I've got another not future in space, Astro Coffee Hangout, where we are going to be. Carol has set it up for me. I've lost the. It's on. What? Oh boy. I can't believe I forgot what it was. We're going to be... No, I don't have it here. Oh, yeah, there it is. Oh, it's about the K2-138 planetary system. That's what it is. And it's where we had some citizen science people, Zooniverse guys getting involved to help us learn about the planets, the Earth-like planets in the K2-138 system. That's tomorrow at 3 o'clock. Back at our Astro Coffee Hangout. So we'll be back then. And I think... the first Future in Space Hangout for the year is going to feature Sarah Seeger and Natalie Battaglia. We're going to talk about TESS.
Wow.
Get an update on TESS.
That's good. I've got her book, Sarah Seeger, Exoplanets.
What's that?
I got her book.
Yes. Sarah Seeger's a rock star.
Very good.
So I'm very happy. She's been in many Hangouts before, but she's also coming back to watch or to be in this one to give us an update on TESS, which she is a principal investigator on. So I'm very excited about that. It should be launching no sooner than, I think, March. So... TESS is coming up, folks. All right, guys.
Cool.
Thank you. It's been another great hangout. I want to thank all of you guys for watching. Thank you for dealing with all of our crappy, stupid internet problems, but they seem to be hopefully fixed. So anyway, thank you all so much for watching. I'll see you guys tomorrow. As always, keep looking up.